Hi everybody, welcome to another of Mrs. John's lesson, and today we are going to look at the concept of center of mass. Like I've said earlier, this topic is linear motion, so this is our booklet, so it's to do with moving objects. Now, when you have objects that are moving over distances greater than their own size. For example, I've got a duster here. It's only this big, but if it's moving over a very long distance, bigger than its own size, then scientists have come up with the concept of a point where all its mass is centered or concentrated. In reality, we do not have point objects because anything is made up of lots and lots of particles, and it is not easy to describe the position and the motion of every individual particle separately. So they've come up with the concept of the center of mass. Now, the center of mass of any object is the point at which all its mass is concentrated. Now you might think, now why are we learning about this? What's important about this? The reason is, if we reduce any large object to a single point, then it's possible to analyze their motion when you're only looking at the motion of that single point, and we can apply Newton's laws of motion to all of this. So it's basically to simplify things. So scientists have come up with this concept. They're very clever, aren't they? So now when we look at, so there's, in this one, we are going to learn, yes, the concept of the center of mass. We're also going to learn about the concept of a system. I had kind of touched upon this when we did momentum in the earlier topic. So a single object can be considered as a system. You can have any number of objects as a system. Okay, when you're talking about a system, we are only considering the motion of the particles within that system, and we're ignoring anything else. Now, when the objects in a system, when they collide with each other, that's called interacting with each other, collision, explosions, they actually exert a force on each other. Now, the thing is, these forces that the objects in a system exert on each other are called internal forces, and they come in pairs. So the force that one object exerts on the other is this equal and opposite to the force that the other object exerts on the first object. And so they cancel each other out. However, if you need to move an object, okay, or a system of objects, then you need to have an external force to move it, to change its state of motion. So that becomes an external force. Now, we talk about a closed system. A closed system is one where you ignore all external forces. And in a closed system, yes, momentum is conserved. Okay. Now, with this concept of center of mass, what we need to know is that, how do we find out where is the position of the center of mass? Okay. Now, the position of the center of mass, if it was a single object, and if it's a uniform object like a ruler, then it's a point about the center of it where it can balance. So it kind of balances on a knife edge. So this is at the 50, if this was a meter ruler, that would be at the 50 centimeter mark. In reality, this is a 60 centimeter ruler, so it balances at the midpoint here. However, not every object is uniform. You could have a non-uniform object like this. So it's pointed here, it's perhaps there. It may not balance in the center. It might balance at some other point which is not in the center. Again, if you have something like a seesaw, and if there is one person sitting at one end, somebody else of a different mass sitting at the other end, then this is not going to balance in the middle, but it's going to balance probably closer to the bigger object, such that the mass of this times its distance from the center of mass is equal to the mass of the lighter one times its distance from the center of mass. So the center of mass is a point between two objects where, if it was like a seesaw, if they were joined together, it's a point where it could be pivoted. There are two ways of calculating the position of the center of mass. So if you have this object here and you have another object here, we calculate distances from the center of mass of the object itself. So assume this dot is the center of mass of each of these. We treat each of them as point masses, that's what it's called. And if there's this imaginary line joining the two of them, it would balance, let's say, somewhere over here. So this triangle represents the center of mass. And let me call this M1 and I'll call this M2. And so all distances are taken from the pivot point or the center of mass. If I call that x1 and if I call that x2, then I get M1 x1 is equal to M2 x2. So this is one way, and you're familiar with this. We kind of learned about this in talks last year when we did year 12 physics. So this is one way of calculating the position of the center of mass. But sometimes it may not be possible to apply this rule to calculate the center of mass. There are other situations where you actually have to use a reference point when two things are moving with relative to each other. So the second way of calculating the position of the center of mass is by using what we call a reference point. So this is using a reference point. So what is a reference point? A reference point is something that stays fixed, which is not moving. The other objects may be moving, okay, which causes a change in the position of the center of mass. So let's say this is like the bank, okay, and let's say that is water. And let's say we have a plank of wood that can float on the water. And let's say we have somebody who's standing there, okay? Now the center of mass of the plank of wood is at the center of the wood. If it was a uniform plank, the center of mass of this girl is somewhere in her center. So with respect to the plank of wood, let's say it's right at the end there. The center of mass of the system is somewhere in between. So if you had to balance that, then where would you hold it, right? So let's say the center of mass of the system, let's say that is somewhere here. I'm just going to put that point. We don't know where it is. So if the girl had to walk forwards on this, what would happen is that the plank would go backwards. Okay, but just to find out the position of the center of mass, we use this as our reference point, the edge of the bank. Okay, because that's not going to move. When the girl walks back and forth, this is also going to move. Okay, all distances are taken from the reference point. So this is XCOM. This is a distance of the center of mass of the system. I'll call that X. And let me call the girl's mass maybe M1 and the mass of the plank itself as M2. And I need a couple more distances. I need the distance of the center of mass of the plank from the reference point. I also need the distance of this girl from the reference point. So I'll call this X1 and I'll call this X2. Okay, so the center of mass of the system itself times the total mass. So that is the total mass times center of mass of the system is equal to the individual masses and their distance from the reference point. Okay, so the distance of the center of mass from the reference point is M1x1 plus M2x2 divided by the total mass. So this is another way of calculating the center of mass of a system when you have a reference point. And later on we'll be doing some questions where we actually need to use this formula rather than the other one. Okay? Right. And what we have to keep in mind is that when there's no external force, momentum is conserved. So if momentum is conserved, that means the position of the center of mass is conserved, because the mass is not the mass of the position of the center of mass of the whole system is conserved. The individual masses are not changing. So even if this Planck moves back and forth because of the girl going back and forth, the distance and the center of mass of the system from the reference point will always stay the same. The center of mass of the system with respect to the Planck may change back and forth, but this distance will stay fixed. Okay, that's something we have to keep in mind, and I will be reiterating this when we do a question later on based on this. So these are two ways of calculating the center position of the center of mass. There's one other thing that you need to know, and that is, how do you calculate the velocity of the center of mass? So this has to do, this is if the whole system is moving, the center of mass of the system is moving as well. And this is to do with conservation of momentum. So if there's no external force, that means that the mass of the system stays the same, and so does the velocity of the center of mass stays the same. So when we say the velocity stays the same, it means the speed is constant, it is moving, and also the direction doesn't change. So in other words, the center of mass moves in a straight line at constant speed when momentum is conserved, when there are no other external forces. Okay, and so how do you find the velocity of the center of mass? So the velocity, because when momentum is conserved, so momentum, the total momentum is conserved. Okay, and the momentum of the system, this is the important thing, is the momentum of one particle plus the momentum of the other particle. Momentum is mass times velocity. So mass times the total mass times the common velocity, which is, this is the center velocity of the center of mass, is equal to the individual momentum of the particles that make up the system. So if I make V, C, O, M the subject of the formula, I will get a formula to calculate the velocity of the center of mass of the system. This is very similar to the formula with the reference point. That was a position. This is a velocity formula. So instead of V in the other one, you had X, which was distances. This is speed. Okay? So, and remember, velocity has got direction, because this is to do with momentum. They're vector quantities. So I will stop here, and I'll make another video with a couple of worksheets we do for this topic.